Welcome back to DemystifySci. I'm Anastasia.
I'm Shiloh.
And this is the place where we search for the theories that are going to change the world. And today we are talking electricity. With us for the conversation, we have a friend of the show, guest at the Demysticon conference in Portugal this year, Koch Torres Assis. He's been on the show 4 times already, if you include his Demysticon appearance. And for the 5th occurrence, we have a real treat. So at the conference, Andre came with an entire bag of experiments. His case is that our understanding of the simplest form of electricity, turboelectricity, where you can take a plastic or a glass rod and you can rub it with either silk or wool or a paper towel, and then show that it either attracts little pieces of paper or repels them, is really, really poorly understood, and that there's a ton of really unintuitive and strange phenomena that are hidden in this super basic phenomenon of electricity that's been known for like more than 2,000 years. And so for this conversation, Andre actually has a series of demonstrations where he shows that our understanding of what constitutes a conductor, what constitutes an insulator, and honestly, like what electricity is, are sorely lacking.
These turn out to be the fundamental experiments that were done that gave us the modern picture of electricity, which, if you don't already know by now, is lacking in many departments. And there's a fundamental paradox at the center of this entire project today, which isn't revealed until the end. And so it kind of gives us a full circle picture of history of how we came to embrace the picture of these little electron bowling balls and why that explanation is fundamentally insufficient at the end of the day as well.
I think it's definitely our most interactive episode so far, and I hope that we end up doing more of them because the experiments that Andre shows are only a small fraction of all of the experiments that were presented to us at the conference. And so I think that this is going to be a very rich vein to mine for some time going forward.
And, this entire project is supported by you guys. We could not do it without you. So if you are already somebody who supports us at Patreon, thank you so, so, so much. You are making it possible for us to spend more and more of our time working on this project. If you are not already supporting the project, I would advise you to consider what we might actually do if we get your support. We have big plans. We want to be able to do these interviews in person, but that costs money. We need to go places. We need to rent rooms. We need to bring equipment. It's actually very, very expensive and difficult to do. But every time we do an in-person interview, it's way, way better than trying to do it across Zoom. We also want to put on more in-person events like Demysticon. We want to be able to have events that aren't just in a conference room. We're thinking about having some sort of outdoor gathering very soon where we just all hang out at a campsite and trade campfire stories that isn't so much an academic program. What else are we going to do with their money?
We want to do a live taping of Paradigm Drift. We want to be able to take this show on the road. Like, we have a ton of people that want to be able to share their ideas with the world, and we really don't want it to be just through the internet. There's something about interactions on the computer that are somehow incomplete. And if you support us on Patreon for 75 cents a week, you power us to be able to do all of these things. And I cannot say enough how important it is that if you value this program, if you value the ideas that we bring, the energy that we provide to the world, come support us at patreon.com/demystifysci.
Really, through like the tiniest donations, this is adding up to the point that we're making this our full-time job, and we want to be more powerful with it being our full-time job. And so I know you have 75 cents lying around on the kitchen table right now. You can probably part with it, and it will make sure that we can do all of these projects to the max in the future.
And speaking of Paradigm Drift, we are recording our 7th edition of Paradigm Drift next month. The link to sign up for that is down below in the description. And for those of you who don't know, Paradigm Drift is the show where we open up the floor for you. If you are a theorist that has an idea about how the world works that nobody knows yet, sign up for a chance to present. You get 60 seconds to give us the absolute most condensed version of your theory, and then afterwards we interview you and our panelist, and we do our best to help you figure out how to present these ideas better, to make them into something that isn't just a general collection of disjointed ideas. We're really, really trying to make sure that this is a place where people learn to talk. And I want to add something. We have had a lot of noise recently about people who have shown up for the last couple of paradigm drifts and they haven't gotten to present, and they're like, we need to do something in order to make sure that the people who keep showing up are the ones that are presenting. And I'm like, I think that it's really, really important to see paradigm drift as a community space. It's not just a place to show up and to drop your theory and leave. The goal is to build a space where people are helping each other with their theories, where in the chat that happens during the recording, everybody's responding to what's actually being said and helping people hone their ideas and helping them figure out what parts work and what parts don't. Because it's not just about having a microphone. It's about having a community.
And to that end, even if you don't have a theory to present, you should totally come hang out for the next taping, because the more people that are in the chat, the more energy there is, the more ideas we have in terms of interacting with the guest that's presenting. So you absolutely don't have to present in order to come to Paradigm Drift, and that would be incredible if you did show up.
Absolutely. But I don't think that there's any other items of business. I think we can get to the physics demonstrations. And so enjoy our conversation with Dr. Andre Koch Torres Assis of the University of Campinas in Brazil, who is going to teach us all about the hidden mysteries of vitreous electricity.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
Yeah, there was a funny afternoon. I think it was one of the last days of the conference. One of our friends came over and was like, "Hurry, Andre's doing magic tricks with electricity in the corner. You gotta see this." And sure enough, like, there's this crowd gathered around a table, and Andre is doing what we were about to do.
Just demonstrating the vagaries of electricity.
Yes. So these experiments, they come from this book, The Experimental and Historical Foundations of Electricity, which was published by a Canadian publisher, Apeiron, some years ago. And I am just fascinated by these topics. So my idea would be to perform some of these experiments live, and they are very interesting. And not only that, but if we have time at the end, I would like to come back to these experiments and to show that there are some very deep mysteries, even in these, which seem to be very simple and old experiments on electricity. They still hide some deep physical mysteries that I hope maybe the people who are watching us now may help solve some of these riddles. The first experiment, which I will do from this book, is also the oldest experiment in the history of electricity. It is called the Amber effect. So I will begin with this oldest experiment here.
Would you say this is the moment that electricity was first investigated as something other than magic, or?
It was just mentioned. It was by Plato in one of his dialogues on Socrates. And
interesting.
So, still magic at this point in history.
Yes, somehow.
Platonic magic.
I just put some bits of paper here. Okay.
Like little pieces of confetti, it looks like.
In the old days in Greece and so on, people, they did perform this experiment with amber. Amber is a fossilized tree resin, which looks like a rock, but it is organic. But now I will do the same kind of experiment utilizing a plastic tube. Okay? And this plastic tube, I will rub it in a paper tissue or paper towel, kitchen paper, and so on. So the amber will be like my plastic tube. Okay, so I will just rub it, the plastic tube, with my.
Now,
paper.
can we rub it back and forth, or does it have to be in one direction? It doesn't matter.
It doesn't matter.
Okay.
Normally, I do that in one direction, but it doesn't matter. So it just happens like that. So you just rub and you attract these light pieces of paper.
Oh, Plato must have been losing his mind.
If I have a plastic tube which was not rubbed, nothing happens. So I don't attract anything. So we begin to attract after we make friction, okay? And normally, if people are doing that at home, it helps if we rub that briskly, fast. So it helps, and then you attract the paper bits.
And what were the ancients thinking? Like, what do we have in the record of Plato's thoughts about this?
Well, Plato was discussing, just to mention that quickly in his dialogue, and he was questioning against the existence of vacuum. So he was saying that in this amber effect, there was no real attraction between amber and the paper bits. So he believed it was like when we breathe, that there is a circulation of air, and somehow the air did maybe when we heat the amber, we create vortices of air, and this air brings the paper bit towards the amber. So that was
So he blamed it on.
he was discussing.
He blamed it on the air, basically. He thought that the mediator was the air, perhaps.
Yes, that was in his mind what Plato did believe. But what we observe is a direct attraction between the amber or the plastic tube and the paper bits. And it's interesting, Shiloh, because this was just a curiosity. And for 2,000 years, we only did that with electricity. And I can attract cotton, paper, dry straw, anything which is light. And even in 1741, a French guy, Desaguliers, he made an experiment in which he had a thin stream of water, tap water, falling, and when he did approach rubbed amber, the water deflects, goes towards the rubbed amber or our tube here. So this experiment anyone can do at home. Just take a plastic tube or an acrylic ruler. We can rub that in our hair, in a cotton, in paper napkin. And when you approach a thin stream of water, it deflects towards the plastic.
That's pretty cool.
So
can I ask you a question, Andre? Have people done this in full vacuum at this point, like in really high vacuum? Does it change anything?
When you decrease from normal pressure, when you decrease the pressure, then air becomes more conducting, which is very strange. So it
Very
is
strange.
you discharge more easily your plastic, anything that you rub. Only when you go to extremely high vacuum, then it becomes highly insulating. But when you just decrease a little the pressure, instead of 1 atmosphere to 0.1, 0.001, and so on, the air becomes more conducting. Only when you go to extremely high pressure does it becomes very insulating again.
That is really, really fascinating.
Yes.
So maybe Plato wasn't so wrong after all. There might be something going on with those molecules inside of the vacuum.
Yes, but you see, when you go to extremely high vacuum, you can do even better this experiment. So
to a point, right?
No, it works. When you decrease the pressure, it's more difficult to obtain the effect. But after you go to extremely high vacuum, you can do it very well, because then air becomes very insulating and you can attract very easily. The plastic tube or your amber don't lose its electricity. So it works very well in extremely high vacuum. But now, for 2000 years, it was just a curiosity, this amber effect. We didn't go beyond that, attracting light bodies. What I will show to you, Anastasia and Shiloh, is the oldest instrument made by man in order to study electricity. It is called a versorium, something which can turn. So it is it's just like a magnetized needle, but I will do it with paper fastener or brass fastener. We just on the head, we make a small deformation with a nail and a hammer so that it does not slip. And I will support it. This is a cork with a toothpick. It can be cork with a pin or a needle. And so this is the oldest instrument. Okay, so this instrument, it has only one piece, which is the brass fastener, which can spin, okay? So once more, I rub my plastic tube and I just get close to the versorium and immediately it begins to turn. I don't need to touch the fastener. I just get close to it and it turns very easily. So this instrument, it was made by William Gilbert.
Is this the very first electric motor on record?
Yes,
very primitive electric motor.
Yes, it is an electric motor. And I am making it moving by my control, okay? I just get close and it spins. And I can choose in which direction it spins. I can reverse it very easily. I don't need to touch. So this is the oldest instrument made by man in order to study electricity. And Gilbert did utilize this instrument it is more sensitive than attracting bits of paper. Because when you attract bits of paper, you need to go against gravity. In this case, the gravity is already supported by the nail or by the toothpick. So you only need to turn it, but you don't need to move it against gravity. So this instrument is much more sensitive than attracting light paper bits.
Mm.
And Gilbert did utilize this instrument in order to find other substances which attract like amber when they are rubbed. For instance, now I will rub a wire made of metal. Okay, I will rub it with my paper napkin and I will get close to my versorium. When I get close, nothing happens. So also I did rub it, nothing happens. When I do the same with my plastic tube, I just rub it, and when I get close to it, immediately it begins to turn. If I stop it here, so the versorium will stop and it will point towards my rubbed plastic. I can control where the versorium goes, okay? It just falls. But if I repeat and rub wire, metallic wire, nothing happens. I can get close to it, it does not move. So once again, so the versorium is made of a single piece, which is the brass fastener or the paper fastener. The cork with the pin is just to support it, okay? But it has only one element which can turn. And so Gilbert did utilize this instrument in order to distinguish two kinds of material. The materials which did attract after you rub it and you can make the versorium spin, he called them electric, because amber in Greek is electron. So all of these materials, they did behave like amber. They were amber-like. So he called them electric. So all of these words, electricity, electron, electrostatics, they come from this Greek word amber. So Gilbert, utilizing his versorium, he could classify. He would call, for instance, plastic, if it did exist in 1600, which was
Yeah,
not
what were some of the
case.
materials that he actually had that came up as electric?
Well, he did try many diamond and other precious jewels, different kinds of wood. He tried many things. And as I showed, when I did rub a metallic wire, it does not spin the versorium. So a metal would be a non-electric, according to Gilbert's classification. So this was the first classification made in the history of electricity.
Do you have any examples though? I still didn't like. Was wood one of them? Like, what were the materials that did behave like amber in Gilbert's day?
Yes, some precious jewels did behave like that, and some kinds of wood as well, especially if they were very dry. But other kinds of wood did not move the versorium, so they were just like metal. All kinds of metal were non-electric.
Got it.
Okay, so this is very interesting. Now I will show you a new phenomena. Okay, and this new phenomena, we need another instrument. And this instrument, which I will show now, has two elements, which is just a paper disc and a thread. Okay, so it has two components, two elements, the paper disc and the thread. And in order to facilitate the experiment, I will utilize what is called an electric pendulum. Now I will do the experiment. So this experiment, it's called an electric pendulum. It's very simple. So it is a straw and my disc, paper disc or aluminum foil disc. I tie it to the end of a plastic straw. My thread, I tie my thread to the end of a plastic straw. And here I have another brass fastener, paper fastener, just to make a pendulum. So it is a pendulum here. And so that I don't need to hold it in my hand, I will utilize a support. So this support is just a plastic coffee cup. I make a hole, and here I have another fastener, paper fastener, and I fill it with clay or plaster. Okay, so when it is dry, it will be the support of my pendulum. Okay, I just put my plastic straw here. It is just a support. Now I can control here, and now I will do the experiment. So once again, when I approach a plastic tube which has not been rubbed, nothing happens. But now I rub my plastic tube in a paper napkin and I come close to it. As you see, when I get close, the paper disc goes towards my rubbed plastic tube. So this is the same as we saw before with the amber effect and with the versorium. But now take notice, because now something new will happen. Now I rub it again, and then I come close, and now it is being repelled by my plastic straw. This is just fascinating. So we see now repulsion. We always talk about attraction and repulsion in electricity, but we never see that in reality. In reality, we always see attraction. But with this electric pendulum, we can see it very easily. You see, if I get close, it is being repelled.
And what's kind of interesting here is that this is a metal, right? Is this a non-electric substance according to Gilbert?
Yes. And in order to begin again the experiment, I just touch the disc with my finger, okay? Now I will begin again. I will rub my plastic tube and get close to it. It is being attracted. It is being attracted. So in order to see repulsion, the key element is to let them touch one another. After they touch, then immediately they begin to be repelled. So the crucial element is to touch. Okay? So this mechanism was discovered after the death of Isaac Newton. It was discovered by a French guy, a scientist called Charles Dufay. He discovered this in 1733. He called this ACR mechanism: attraction, contact, and repulsion. He didn't utilize a pendulum like that, but in another kind of experiment, he found this mechanism. This pendulum shows it very easily. So this is very important. So I will repeat it once more. So to begin, I just touch with the paper disc with my finger. So if I rub it and come close, it comes toward my tube. Okay. If I let them touch after they get in contact, so immediately they begin to be repelled. And
Now, do you want to talk about
repulsion.
what's actually happening here, or do you want to circle back on that after we make it through all of these experiments?
In this case, we can talk. It is just when, suppose that my plastic tube is negative. When I get close, the charge in the paper disc, they polarize. And when they get in touch, the opposite charges, which are in the side close to the tube, they neutralize. And so the disc becomes acquires a charge of the same sign as that of the tube. And so they begin to repel because both have charge of the same sign.
Well, so there's something interesting here, which is as I'm doing this, if you bring the tube sufficiently close to the disc, it does still attract. So like even after you put them into contact, and then you bring the plastic tube close to the disc will stick to the plastic tube still.
And this is fascinating, Anastasia. And this was shown by Dufay himself. Even in this case, for instance, they are being repelled because both have charge of the same sign. Let us say it negative. But if sometimes, even if you get very close, sometimes they touch one another again. And even when both have net charge of the same sign, when you get close, you are still polarizing the other charge of the disk. And sometimes these polarized charge, they will be attracted by the negative tube, and the negative charge in the disk will be repelled. And sometimes the attraction due to this polarization, especially when the distance is very small between them, they can be stronger than the repulsion between charge of the same sign. So sometimes we see attraction even for two bodies which have a net charge of the same sign.
How much of this did Dufay I'm sorry. How much did Dufay understand about this? Like, was the terminology charge starting to be circulated?
No.
How were they thinking about this?
Everything came later. He just discovered this mechanism.
I think Dufay was the first to propose that there were two electrical fluids. And
yes,
so he was the one that came up with the idea that there was vitreous fluid and resinous fluid.
Yes, but that came after this discovery.
I see.
So at that moment, he just discovered a new phenomenon in electricity, which was repulsion.
But the way
for 2,000 years, no one saw repulsion.
Okay,
As I showed to you before, sometimes I can attract bits of paper in the amber effect. But didn't it touch and repel? Sometimes it did repel. But as the bits of paper did fall to the ground, people thought that it went to the ground because of gravity, not because it was being repelled by the amber. So people didn't recognize repulsion as an electrical phenomenon. The first to recognize this was Dufay with this mechanism that you can also have repulsion in electricity if you let them touch. And this, you see, came after Isaac Newton, Anastasia. This is just fascinating.
If I can add something here. So at this point, as far as I understand it, so Francis Hauksbee has been doing these like vacuum demonstrations where he has these glass spheres, he fills them with mercury, he can spin them under vacuum, and then the mercury inside of them dances and it produces this like strange glowing light. and he has another generator where he has like all of these strings, and then he spins the outside sphere, and then the strings will kind of align themselves orthogonally to the sphere, and they've contextualized electricity as being some kind of effluvium, something that flows through the substances.
It was just some material which maybe it was ejected by your rubbed amber or by your rubbed glass or something. It did emanate from your rubbed piece of amber, and somehow it was this effluvium, this medium around here which exert all of these effects. But it was not yet clear, this repulsion, electrical repulsion. It only became clear with this discovery of this attraction, contact, and repulsion by Dufay after the death of Isaac Newton. But now, Shiloh, I will try, it does not always work, a fascinating experiment here, which is a similar one. This experiment, let us see if it does work.
Is Dufay and Gilbert, are they speculating about anything in the way that Plato was? Do they think that it's the air, or are they playing with do they still have an ether conception at this point in time? Is there any discussion in the literature?
Yes, Shiloh. As Anastasia was saying, sometimes they did had this idea of this effluvium, this material which was ejected by the rubbed piece of amber or rubbed glass tube and so on.
I got it. So it's like a fire hose kind of mechanism.
Yes. It's a kind of contact, action due to contact with this kind of material. It was maybe it was like air or something which was emitted by the rubbed amber or something.
Got it.
But now this is a fascinating experiment. Here I have a dandelion seed. Okay, I just let it fall, and I will let us see if the experiment works. In order for the experiment to work, we need to say the correct words. Wingardium Leviosa.
Oh, I thought you were going to say abracadabra.
It can also be abracadabra, but in modern times it is Wingardium Leviosa. So let us see if it works. So I just let it fall, and then it is in my tube, okay? I'll try to. Oh, it is falling again. I rub my tube. Just once more here. Okay. I will try a few times. Yeah, almost there. Wingardium Leviosa. Okay, here we are.
Wow.
As you can see, I am levitating the dandelion seed. I will bring it closer to the camera.
It's amazing.
Okay. This experiment, it was made before Harry Potter by Garrick of the air pump, then by Stephen Gray, and then by Dufay. Okay. I can let it go down and I can control it here. Okay.
Is this the same attraction, contact, repulsion mechanism?
Yes, exactly, Shiloh. First, the dandelion seed is attracted by my tube. Then it gets in touch, acquires a charge of the same sign, then it is repelled. Then I can levitate it. But now I will try to show something even more remarkable. As I said, it does not always work. Let us see. I will repeat the experiment. Still here, my tube.
2 attractions.
This attraction, contact, and repulsion. Sometimes it needs to take a few times before we see
That's number 3.
repulsion. It's almost there. It's
Number
almost
4.
going up alone. Now I believe it will go. Yes. So now I am levitating it again, okay? Let it go down, okay? But now, as you can see, I can also levitate it from above.
Whoa.
That's quite new.
Hmm.
I can levitate it from below. Oh, it did go to my screen. I can levitate it from below, like here, but I can also levitate it from above. From this one here. This
Did you rub the other
fantastic.
tube?
Sorry?
Did you rub the other tube?
Yes, I did. And I can explain to you first how I did it, and then what was the importance of this experiment. When I am levitating the dandelion seed from below, I am utilizing this plastic tube, which I did rub it with a paper napkin. I could also rub it in my hair or in my cotton shirt. With anything, it becomes negative. And then the dandelion seed is attracted, touches the tube, and it is almost going up here. Oh, it did go alone by itself. And then it is repelled, okay? But how could I attract it from above? From above, I did have another plastic straw, and in this one, I did rub it with plumber's tape, which are in my finger. It's also called Teflon, Teflon tape, or seal thread tape. It's a plumber's tape, okay? Because this is Anastasia and Shiloh. This is one of the curious and difficult things to grasp. It is very easy to electrify plastic negatively with any material that we rub. I can rub it with paper, silk, cotton, aluminum foil. With anything, the plastic tube becomes negative with a good amount of negative charge. But in order to attract it from above, I need to have my plastic straw or my plastic tube charged positively. And it was only by trial and error, trying many different kinds of material, that I discovered that with if I rub it like in my fingers, I have this plumber's tape here. If I rub it like that, it becomes positive.
So just to catch people up who aren't electricians and so forth, the standard way of thinking about this is that if it's negatively charged, it's got an excess of electricity. It's
Yes.
got an excess of electrons, and if it's positive, it's missing these. So something about the Teflon is at least by convention is stealing the electrons, right?
Yes, but you see, Shiloh, the important thing here is that when the person who made this discovery was this Charles Dufay, that was in 1733. Isaac Newton was already dead by that time. And what did Dufay? He had discovered this attraction, contact, and repulsion mechanism. Okay? That you touch and then you begin to be repelled. Just like my pendulum or my dandelion seed and so on. And Dufay, he was rubbing a glass tube. And he was floating a very thin gold leaf. And then he did it, he was levitating the gold leaf, just as I am levitating here this dandelion seed. And then he did rub another glass tube. And both of them, they did repel the dandelion seed. But the dandelion seed had touched only the first glass tube. But if you rub another glass tube and you approach, it will also repel. Okay? So everything was in place according to this attraction, contact, and repulsion mechanism. But then one day, when he was just levitating his gold leaf, he did rub resin. And then when he approached the rubbed resin to his floating gold leaf, the gold leaf did go towards the resin immediately. And to him, he was completely surprised. And it was this experiment which made this Dufay postulate the existence of two kinds of electricity. It was this experiment, this Harry Potter experiment. It is just fascinating. If you allow me, I will read here the words of Dufay, 1733. He said the following in his paper: I began by floating in air a thin gold leaf by this attraction, contact, and repulsion mechanism. Then he continues. Then he did approach this resin, and the gold leaf did go towards the resin. Then Dufay continues. But what disconcerted me prodigiously was the following experiment, this one which I just mentioned. Dufay continues. I confess I had expected quite the opposite effect, because he expected everything to repel the floating gold leaf. Then he continues. This made me think that there were two different kinds of electricity. I will call one of them vitreous electricity. That is what we call nowadays positive electricity. And he continues. And the other I will call resinous electricity. That is what we call negative electricity. And he continues. Both kinds repel the bodies which acquired an electricity of the same nature as that of their own. On the contrary, they attract the bodies having an electricity of a different nature than their own. So that is what we learn in school, that there are positive and negative charges. Positive repels positive, negative repels negative, and positive attracts negative. But when we learn that in schools, we learn that in high school. We imagine that this was known by the old Greeks 2,500 years ago. This is not the case. Isaac Newton, the great Newton, didn't know that there are two kinds of electricity. This is crazy. Crazy, crazy, crazy.
What was the reception at the time where people bought,
The science... Sorry, Shiloh?
Oh, what was the
Sorry.
reception of this idea? Was it compelling to people? Did they immediately start to think of electricity as having two forms? What was the climate of the community?
No, it was not that easy, Shiloh. A few of them did accept, but then it was forgotten again. Then only several years later, with another scientist, Seymour, who made these experiments with silk socks, which did repel or attract one another. Then once again, he spoke about two kinds of electricity. Benjamin Franklin, who utilized this nomenclature that we utilize nowadays, positive and negative, he didn't believe in two kinds of electricity. To Franklin, there was only electrical matter. And paper materials which had the normal amount didn't attract nor repel one another. When they have an excess of one of them, or
deficit. Deficit,
yes.
And this is closer to the way that we think about it today, it seems like, or the way that it's generally treated in electrical engineering.
But nowadays we speak of two kinds of electricity, positive and negative.
Kind of. I mean, isn't it just the excess of electrons or the deficit of electrons still?
Yes, but it might be, I can have an excess of protons in one, an excess of electrons in the other, they will attract.
I gotcha.
If I have an excess of electrons in both of them, they will repel.
Yeah, so, Franklin had this he had an equilibrium model. He was basically if there's a and so like two substances that were depleted would repel one another. Two substances that had an excess would repel one another. But then if you took a substance that had an excess and a substance that had a deficit, then you could put them next to each other, and the action of this fluid going from one to the other would produce the electrical effects observed.
Yes, but you see, he didn't. He had not only Franklin, but all the Franklinists, the other who did follow him afterwards. They did have a great difficulty in explaining repulsion. Okay, they could not explain repulsion. But anyhow. So what I want to call attention is that the great Isaac Newton didn't know that there were two kinds of electricity. He only knew, just like everyone before him, that if you rub something, you attract materials. He only knew that. He didn't know about two kinds of electricity. Isaac Newton didn't know about conductors and insulators. Everything came after he was dead.
Did he make any attempts to explain it? Did he make any?
Very little ones, because he never dealt deeply with electricity. He only described some experiments in his book Optics when he was polishing glass lenses, and then sometimes he did electrify the lens, and so sometimes he saw these brass being attracted and contacting the lens and being so it was just, as Anastasia said, some kind of effluvium which was emitted by the lens, and this effluvium was around and moving like air, and that would move the paper bits or the brass bits and so on. But only very briefly. He never made the real experiments on electricity. So these crucial discoveries, they were made after the death of Isaac Newton. So this is fantastic to know, and also to know how were they made. It was just with this Harry Potter experiment. Yes, Anastasia?
Why is it so significant to you that this was made after Newton's time?
Because the science of mechanics goes back to the Greeks, Archimedes, and the statics, or the principle of Archimedes, the law of the lever or the lever. So that goes back to Archimedes, 2,300 years ago, very old science. Archimedes made calculations of areas, centers of gravity. So the science of mechanics was very highly developed at that time. But on electricity, we only knew amber for 2,000 years. So the whole development did begin after Newton on electricity. Not in optics, not in astronomy, not in mathematics, not in mechanics, but in electricity, it was just a curiosity. And even magnetism was developed by the Chinese and so on because of the compass needle and so on. But for electricity, it was just a curiosity because we only knew the amber effect, only.
And so you're basically just making this point that it's a relatively new if you were to take the whole of physics, you're basically making the point that, look, most of these things we have been working with for thousands of years, but it's only electricity that is about, I don't know, 300 years old, if we're being generous.
And why? And that's the point. And to explain why, I need to make another experiment.
Excellent.
So the other experiment, I will need another instrument, okay? So I already showed to you the attraction, contact, and repulsion, and the two kinds of electricity. Up to now, I showed to you two instruments. One was the versorium, which has just one element, which is the brass fastener, which can spin. The second instrument was the electric pendulum. I can do the experiment here in my hand. So I have only a thread and a disc. So I will just repeat it here. I don't need the pendulum, just to show that, you see? I see the repulsion here in my hand. So this second instrument has two elements, the thread and the disc. But now the third instrument, which is the most important one, has three elements. I have a plastic straw here. I have a cardboard here. And I have a strip of tissue paper or kite paper. It is glued only at one extremity, okay? The other one is free, okay, it's free to move, okay? There is glue here. So it has three elements. So this is called an electroscope. So that I don't need to do the experiment in my hand, I will utilize once more a support, which is my plastic coffee cup with a paper fastener, and I fill it with plaster or modeling clay, okay? And then I just put it here, okay? So this is called an electroscope. Now I can do the experiments to show to you. So this is just my electroscope. Plastic straw, cardboard, and kite paper or tissue paper strip. Okay, and here's just my support. Okay, so that it stays in place. Now I will make the experiment. I will once more rub my magic wand to make another spell here. So if I just come close here, I will attract the paper strip, okay? I can attract it very easily, just as the same. But now I will do, this is not the most important experiment. What comes, the most important experiment comes now. What I will do now is that I will scratch with my plastic rubbed tube the cardboard. I will stretch it here, okay? When I scratch it here, the tissue paper strip goes up, okay? I am electrifying my electroscope, and it remains electrified, okay? So the first thing that we can do with the electroscope is to electrify it. But now comes the most important experiment that I will show today. Please take attention. When it is electrified, I will touch the cardboard with, say, another plastic tube, a plastic straw. Nothing happens, okay? Nothing happens. It just stays there. But when I come and touch the cardboard with a metal wire, take a look at the strip. When I touch it, immediately it goes down, and I can remove it and the strip is down. I will repeat this experiment. It is the simplest experiment of today, but it is the most important one. So once again, I rub my plastic tube and I scratch it here. And then the strip goes up. And then I will touch the cardboard with a plastic straw. Nothing happens to the strip. Now I will touch it with a metal wire. Immediately the strip goes down. This discovery, to me, it is the most important discovery in the history of electricity. It was made by an old guy, contemporary of Isaac Newton, but it was made just after Newton's death. His name was Stephen Gray, Gray. He didn't make the discovery as I am showing here. This is just a didactic way to show the experiment. And with this discovery, we can make another classification of the materials, which are insulators and conductors. Insulators, they are just my plastic tube that they do not discharge the electroscope when I touch it. And conductors, just like my metal wire, are the materials which discharge my electroscope when I touch it. So I will just repeat it once more because this is a very important experiment. Let me make it.
And just to keep score here, these are the materials that Gilbert would have called non-electric materials that are conducting.
Yes. But now it is a different way of classifying them. What we call insulators are the materials which Gilbert did call electric. And what we call conductors are the materials which Gilbert did call non-electric.
And this is really it's an interesting dichotomy too, because the electric materials sustained the charge, right? But the non-electric materials, they wick it away, they conduct it away, right?
Yes, you can sustain them. We can come back to this, but in order to do it, it's tricky. So I will repeat the experiment, okay, Shiloh? So once again, I rub my plastic tube. The first step is to electrify my electroscope, okay? So the strip is up, which means that it is electrified. Now I touch my cardboard with plastic. I can touch everywhere. I can even touch the strip itself. nothing happens. It continues electrified. We'll try it more. Now I will touch the cardboard with a metal wire. As soon as I touch, immediately the strip goes down and it remains down. This is the simplest experiment that I'm showing today. But it is the most important one because this classification of conductors and insulators is the most important classification that we can do of bodies in nature.
Is that because it's functional, or why do you think it's the most important?
Because, for two reasons. First, because it continues nowadays. The other one by Gilbert has been forgotten. I can come back to that later on. But this one still is in place and it will continue forever because it is very important. And the second reason, Shiloh, is that it was this discovery which allowed the control of electricity.
Mm-hmm.
Only after we did discover conductors and insulators could we store electric charge, be it positive or negative, and could we conduct electricity along power lines, which are made of metal and so on.
Anastasia's just discovered a new feature here, which is that she's holding the metal with an insulator and she's unable to discharge the scope still.
Yes. So in order to discharge, I need to hold it by my hand, just like here.
So something that was really interesting, though, is that when you were discharging it, you were holding the piece of metal with the Teflon tape. Right? Like it was in your hands, but the fingers that were holding it were covered in the Teflon tape, and it still discharged the electroscope.
Yeah, I didn't realize that, but it's not so simple because it's very thin, and so I need to see that later on.
We're gonna have to circle back on the Teflon tape. That's a mystery still.
Luckily, we have we have the Teflon tape as part of the kit.
Yes, I did put that in my experimental kit, which I gave to you in Portugal this June.
Okay, so let me ask you this. What was Gray thinking about this at the time when he made this discovery?
Gray was partying. Gray's story is crazy. So he was kind of an acolyte of Newton. So he was kind of in the circle of Newton. And then he fell on hard times. He was
not so close to Newton. He was close to Hans Sloane, another guy who became important in the Royal Society. But Gray himself, he was not educated at the university. He was a dyer as a profession, and he was a very poor guy. And when he made this discovery, he was living in a charitable home for poor people. He went there with 53 years old, and he lived there until he died with 70 years old. And this discovery was made by Gray when he was 65 years old. It is rare to see these important discoveries made by old people. Normally they are in their 20s, just like Newton or Einstein and many other cases. But in the case of Gray, he was an old guy, and he was a very poor guy living by the state or by the donors of this charitable house, like many others. And he died in poverty, and completely poverty. But he had some connections with the Royal Society. For this reason, he could publish some of his papers, not only on electricity, but he also made observations of comets and things like that in astronomy. So he published a few of his papers. In electricity, he published 10 papers. And but now I want to continue just to close the circle, okay?
So he
And
was
to
still on the
continue.
just to make sure we catch this. So he was on the effluvium side of things. He was going with Newton's ideas.
Yes. And this discovery was quite a surprise for Gray as well. He did believe that when he did rub, he was making experiment with a glass tube. And when he did rub it, he did believe that maybe the electricity would go out radially. But to his surprise, he did discover that it did go out longitudinally with anything which he did connect in his glass tube. He did connect a cork, then a piece of wire, and other things. And everything became electrified in the end. He did rub only his glass tube. So it was quite a surprise to him. But now I will make here a list of 10 different materials. And I would like everyone who is watching us now, Shiloh, to make a prediction. And then I will make the experiment. Okay? And first, write in a piece of paper. Divide a piece of paper in 2 columns. One, you write insulator. The other, you write conductor. As insulator, you can put plastic. As conductor, you can put metal. As we saw here, okay? The plastic did not discharge the electroscope, and the metal discharged the electroscope. So metal is a conductor, and plastic is an insulator. Now I will say 10 different materials, and each one who is watching us should put the material in the column of insulator or conductor, as you guess it, okay? So, the first material, the human body, okay? Second material, rubber. Third material, wood. Fourth material, glass. Fifth material, paper. Sixth material, cork. Seventh material, cotton. Eighth material, silk. Ninth material, amber. And the last one, 10th material, water. Not sea water or salty water, but fresh water from the tap, from the faucet, okay? Or mineral water that we drink, okay? So I will repeat, and then I will give a few minutes for people to classify. Who is watching me can stop the video for a few minutes after I say it, but please try to make the predictions. It is very important that each one who is watching now makes himself the prediction, puts each of these material in one of these columns. Later on, we will see the answer, okay? If you wish, you can also do the predictions yourself. It's not necessary.
I'm on it. I was looking for a pen, but I got it now. All right, let's go.
But I would like everyone who is watching us to put the material. So once again, human body or our skin, first. Second, rubber. Third, wood. So you put either insulator or conductor, okay? Wood. Fourth, glass. Fifth, paper. Sixth, cork. Seventh, cotton. Eighth, silk. Ninth, amber. And 10th, fresh water. So who is watching us on the internet, stop the video and please write down in your cell phone or in a piece of paper these 10 materials. I remind you, insulator is plastic, conductor is metal, okay? Everything which will discharge the electroscope will be a conductor. Everything which does not discharge the electroscope will be an insulator. Stop the video, make these 10 predictions, and then continue to watch the video. Okay? So now I will do the experiments. Okay?
Let's go.
Can I go on, Shiva?
Absolutely.
Okay.
Should I give everybody my predictions?
No,
I'll go
you can keep your prediction secret.
All right.
Only for yourself. You don't need to tell them.
I'll tell you the score afterwards.
Okay. I don't know if Anastasia made predictions or not, but it's not necessary.
I've lodged them.
Everyone who is watching us to make these predictions. So let us begin, okay? I always do the same. I always begin electrifying my electroscope. So the first is the human body. I will touch it with my finger. So my finger did discharge the electroscope. So the human body is a conductor. Okay?
Got that one right.
So,
yeah, as expected.
Okay, yes. Now rubber. I will make it with two different rubbers. One is a flip-flop sandals, okay, which is made out of rubber. I just touch it here. Discharge.
Wow.
So I will now make with a different piece of rubber, okay? Now I will take, first I electrify it, and I take it, this is an eraser, okay? I just touch it here. Discharge. So both kinds of rubber are conductors, okay? So let's go on. Wood. Let us see with wood. I have here with me a wooden barbecue skewer. Okay, in Brazil it's very popular. Okay, I just touch it here. Discharge. So wood also conductor.
Got that one wrong too.
So let me continue. After wood, let's go with glass.
I'm gonna have to get my dunce hat out soon.
Mm-hmm.
So the glass here, it's just a glass cup. Okay, I just touch it here. Discharge. So glass also conductor. So now paper. I will touch with three different kinds of paper. Okay. The first is an office paper, letter or A4 paper. Okay. Touch it here. Discharge. A different kind of paper, which is cardboard. A cardboard, okay? I just touch it here. Conductor. A third kind of paper, which is tissue paper or kite paper, which is this one here, which in Brazil we utilize to pack candies, okay? Tissue paper for kite paper. I just touch it here. Conductor. So all different kinds of paper, they are conductors.
Wow,
now
I'm failing this test pretty bad.
Now cork.
Nastia, are you failing this exam as well?
Now cork. I just touch it here. Discharge. So cork is also a conductor. So it is a cork stopper. Okay. Now cotton. So cotton, I have a sewing thread here with me. Okay, I will just take the sewing thread and I will just touch it here. Conductor.
Finally, I got one right.
So cotton is a conductor. Now silk. So silk, I have a silk roll here, okay? So a thread made of silk. I will do the same. I will touch it here. Nothing happens. So silk is an insulator. If I touch it as I did with cotton, immediately it goes down.
We got that one wrong too.
These two. I will just repeat these two so that you can be sure. I electrify it here.
I'm clearly not an electrical engineer.
So
Nasi
I
looks
touch
really
it
concerned
with
over here.
silk. Nothing happens. Okay, nothing. If I touch it with cotton, immediately it goes down. So cotton is conductor and silk is an insulator. I don't have amber here with me, but amber is also an insulator. And the last one, which I will do the experiment, is with water. I have here, I hope you can see, a glass of water, okay, fresh water. I will electrify my electroscope and I will touch only a corner of the cardboard in the water. I will not touch the glass, just a corner, so it is electrified, okay? I will touch just the water with a corner. Immediately it goes down. I will repeat it.
Nice, I got
with
that one.
Water. First, I electrify. So it is electrified, it is up. And I will just touch the corner of the electroscope in the water, not in the glass, only in the water. Immediately it goes down. So this ends the experiment.
Well, I got a 40% on that exam, Andre. I think I'm going to have to retake this class.
I think you are wonderful, Shiloh, because normally people make 90% mistakes. 90%.
It is surprising. Yeah, I'd always, especially the rubber one. I think I'm under this impression. I've heard that cars insulate you from, during lightning strikes or something like this. But I guess car tires aren't rubber. Yes. They're made out of petroleum. So maybe that's different.
But so these are the experiments which I would like to show for the time being.
Pardon the interruption, but I have to ask you for a favor. If you were listening to this program, or if you listened to some other programs of ours and you're like, man, this is a really incredible venue, then I have to ask you to come over to patreon.com/DemystifySci and sign up to support the project. We are very, very, very intentionally avoiding sponsorships and advertisers because we believe that this is not the way to present ideas. I do not want you to be listening to this podcast and then get ads for sports betting and boner pills and like weird electrified mattresses. I want this to be a place that is maintained as hallowed ground for ideas. And if we're going to do that, we need your help. Come over to patreon.com/DemystifySci today and help us power this ship. Okay, so what I did was I collected a couple of different pieces of metal. I got a spoon. I also got gloves, just in case. So I got a spoon, and I wrapped the end of it in electrical tape. And then I got a screwdriver that has a plastic handle. And also this little brad. And so if you put the brad onto the electroscope while you're holding it in this plastic straw, the electroscope does not go down. If you're holding it in your hands, it does go down.
Yes, correctly.
If you take the screwdriver, it still doesn't go down. But then if you take the spoon, which has, I think, more metal, like it's heavier than the screwdriver, the spoon, even insulated, will cause the electroscope to go down. Okay, so that kind of makes sense. Like the metal is a conductor.
Yes, because when we touch that with our hands, as we are conductors, we are grounding. So we work as a ground ourselves. So when we touch a metal wire with our hand and touch the charged electroscope, it discharges through the metal, then through our body and goes to the ground.
Exactly.
Okay.
And so,
and for this reason, Anastasia, for 2000 years, people were trying to electrify metals for many different ways. They were trying just like that because they thought maybe it is friction. Okay, it didn't work. You don't attract bits of paper. You don't spin versorium and so on. People made different ways trying to electrify metal. They put it in the sun with a glass to concentrate the rays of the sun to heat the metal. Didn't work. They did put the metal in an oven, bring it, and didn't work. It didn't attract anything. They did put it in a lighter or below a candle to heat it, maybe to open its pores so that this effluvium would go out and it should attract bits of paper. For 2000 years, no one could, because they didn't know conductors and insulators, and they didn't know that we ourselves are conductors. So it is possible to electrify metals, but you need to hold it in an insulator handle. That is the crucial. And for this reason, this discovery by Gray is the most important one in the history of electricity, because only after you did discover insulators and conductors can you control, store electricity, move it around the wire, communicate, and so on. But you need to isolate from the ground. Otherwise, nothing of these effects will take place. And it was this poor guy, after the death of Isaac Newton, who made this most important discovery. And we don't even hear about his name in the textbooks on electromagnetism. Never. Sometimes Franklin and so on, but Gray, very seldom. But to me, he made the most important discovery of them all.
Okay, so I think that you're right that these pieces are missing, but I'm just, even with the things that you demonstrated, which is that these pieces of these substances,
rubber, wood, and so on.
My question is, like, is it possible that the reason that they behave as conductors in this condition is because they're partially hydrated?
No, maybe, but that's not the main reason. Before I go that, I just want to clarify. I made on purpose the experiments with a.
And there was something else before we move on from this. I have a silk scarf, which I think I'm sitting on. Okay, so I have a silk scarf, and I took this scarf and I put it on the electroscope, and it doesn't immediately take it let the piece of paper come down, but if you touch it several times, then it does come down. And so I think that there's something about the bulk nature of the substance, where if you have enough of it, there's a sufficiently large reservoir that charge can leak to it.
Yes, not only that, but sometimes these materials, even when they are called silk, they are a mixture. of silk with some other material. So it's not that easy. So each one should try their own materials. As I said, I made with wood, but I don't know which kind of tree does it come from. Depending on the kind of wood, or from different species of plant, or if it is drier or more humid, it can behave as conductor, insulator, and so on. So we need try different, because all of these materials, they change from composition and the way of production. And these changes can affect their properties as conductor and insulators. But as I said, I made on purpose the experiment with a cotton sewing thread and with a silk thread. This one was conductor, discharge the electroscope, and this one was insulator. In order to make the electric pendulum, the thread is not only to support the disc against gravity, it needs to be made of an insulator. Otherwise, it will not work. So also this instrument may appear simple. It has already a lot of knowledge in it. So if I hold like here is another, if this thread is made of cotton, and if I rub here my plastic, it will not happen the attraction, contact, and repulsion. It will only take place if the thread is an insulator, like silk. Otherwise, the charge of the disc will discharge through my hand. So in order to make an electric pendulum, the thread needs to be an insulator. It cannot be a cotton thread. So I am explaining this to the audience, people who are watching us, because it's not so simple. You cannot make it with cotton because cotton behaves as a conductor. It can be silk, polyamide thread, polyester thread, or nylon thread, a very thin nylon thread. But it cannot be made of cotton. Otherwise, we will not see all of these, what I showed here today.
I guess the point that I'm trying to make is that I wonder if the substance that is causing these conventionally non-conducting substances to appear as if they are conducting is not the substance itself, but it's the water that's inside of the substance. And so if you were to if you were to take a very, very hard wood, because the skewers are made out of bamboo, which is like a very porous wood that absorbs water easily from the environment. And so the reason that it's able to take away the electricity that's inside the electroscope is not the substance necessarily itself. Like if you were to have the pure substance, it has to do with the fact that there is a continuous chain of water molecules. And so in all cases, the thing that is conducting is not the substance itself. It's the water that is lodged in the matrix of the substance. And if you were to dry it fully, it wouldn't do it.
Sounds like a hydration solid to me.
What did you say?
Sounds like a hydration solid.
Yeah, definitely.
You have a very good point, Anastasia, and that's correct. For instance, as I said, glass, a glass cup, it behaves, normal kinds of glass like this one, they behave like conductors, but I can make it behave like an insulator if I heat that in a microwave oven or in an oven, normal oven, because it is hydrophilic. So it acquires a very thin layer of water on its surface. So its conductive properties is not due to the glass itself, but to this very thin layer of water. So this is a very good point. But there is another point which is much more important. But before going there, just to, as we now know that paper is conductor and plastic is an insulator, then we can see that even, which seems very simple, this electroscope, in order for it to work, the most important thing is the plastic straw, because it is the insulator which permits us to store charge in the cardboard and in the tissue paper strip. If I did support, because this is not only a support, the crucial aspect is that it needs to be an insulator. If I make another one with a wooden stick, skewer, it will not work, because when you scratch your plastic tube here, immediately the charge will discharge to the ground if I make it with a wood skewer. So the most important thing is that this needs to be an insulator. And another thing, these two things here, they must be conductors. For this reason, I made them out of paper. And paper, as I showed just before, they are conductors for electrostatics. So this instrument, which seems very simple, has a lot of science in it. So the straw must be an insulator, and these two must be conductors.
So can we talk about what's the fundamental material difference between these substances? I mean, obviously the hydration is important, but
yes, the hydration is important, very important. But more important than that is another aspect. All of these materials, as we made experiments here, metal, human body, rubber, wood, glass, paper, cork, cotton, they are all conductors. However, this happens for these kinds of experiments in electrostatics. If I make the same experiments with current, I have a battery, 3-volt battery, connect that with a piece of wire, then I let a space before I close the circuit, and in this space I can put different materials. When I connect this space with a conductor, the light bulb turns on, if I have a light bulb and a battery, okay? If I connect this space with an insulator, the light bulb does not turn on. But for these low voltage circuits, like 3 volts, 10 volts, or even 110 volts, like in our homes, the sockets in our home, 220 volts, this socket or outlet in our homes, most of these materials, they behave as insulators. Only metal behaves as conductor for low voltage and for high voltage. But rubber, wood, glass, paper, cork, cotton, they all behave as insulators for low voltage differences. Like when I have a battery of 3 volts, or in our home socket or outlet, 110 volts or 220 volts, these materials, they behave as insulators. In electrostatics,
don't they behave more like resistors than so it's like, because technically I think that you can, I mean, what happens to the substance is that the substance under voltage breaks down, right? So if you were to take a piece of wood and stick it into a circuit that has a 110 volt power supply, I'm pretty sure that wood would just burn up.
A little, yes. But there are other materials which would not burn out. So there is resistivity, but it is more important the behavior as conductor or as insulators. It may seem strange, but in experiments of electrostatics, just like these ones which I just showed to you, we are dealing with extremely high voltages. 1,000 volts, 10,000 volts. It's crazy. The amount of charge, the amount of current is very small, but the amount of voltage between my electroscope and the ground is sometimes easily 10,000 volts. And so for this reason, when I touch anything with my wooden skewer, if I touch it here, it discharges, because for 10,000 volts, my wood behave as conductor. But for 3 volts, it will not turn on a lamp. So the most important aspect is that we, in the textbooks, we learn some rubber, it is an insulator. Water, it is fresh water, is an insulator. This way of expressing is not correct. The correct way of expressing would be these materials behaves as an insulator for low voltages and behaves as a conductor for high voltages, 1,000, 10,000 volts. For 3 volts, 10 volts, sometimes even 110 volts, most of these materials, they behave like insulators. And these we don't learn in the textbooks, which is a pity, because this is the most crucial difference. It's not that the body is an insulator or is a conductor. It behaves as an insulator for low voltage, and it behaves as a conductor for high voltages. This is the most important difference.
It's got to be more complicated than that, right? Because super high voltage transmission lines use glass insulators, and we're talking about like 100,000 volts on that transmission line. And these glass discs linked together are used as insulators on those lines, right? And so if the case that you're making is that the reason that it's capable of conducting is because the voltage on the electroscope is sufficiently high to actually conduct, and in a low voltage circuit it's not, then that sends me down this rabbit hole of, okay, well, what's happening on high voltage power lines that are carrying 100,000 volts where they're using glass insulators or ceramic insulators, right? So there's like
and normally they utilize ceramic insulators, very specific materials.
I mean,
which just like plastic. This plastic here for 10,000 volts behave as an insulator. Ceramics, so it is very specific materials.
I want to talk about what's different at the material composition at the molecular atomic level between the ceramic and the metal, or the ceramic and the hydrated wood. Like, what's going on that makes these materials behave differently?
Well, I know this aspect which Anastasia mentioned about the water is another relevant aspect, because as I showed here, fresh water behaves as a conductor, and many materials, they are hydrophilic. They absorb a very thin layer of water in their surface. And so sometimes these materials, they behave like conductors, not because of their property themselves, but because they acquire this very thin layer of water, and water conducts electricity.
But I guess my question is, can we think about what it is that makes a conductor conduct versus an insulator? Like, what is the fundamental material difference? What's happening?
That I don't know.
Okay. Well, I mean, I guess it comes down to there's something different between the atoms that are composing one versus the other. And there's something about the atoms in the insulator which prevents them.
Especially, Shiloh, about the electrons, which if they are, as we say, free electrons in a metal, or which can move through the material, okay? In a pure insulator, the charges only separate at a molecular level, but they don't pass from one molecule to another in a pure insulator. In a conductor, on the other hand, the charge move throughout the material.
Yeah, that's a really interesting mystery to me. I mean, because you can have an insulator which has metallic atoms in it, but it, like a ceramic, for instance, right, that may have metallic atoms, but they're bound in a molecule such that they're no longer capable of doing that process.
Yes, because the ceramic prevents the transfer of electrons from one metallic atom to another one. You put an insulator between them. So
Yeah, so I was looking a little bit more into this, and so glass insulators are used on voltage lines up to 1,000 kilovolts, and it's a special kind of glass. It's a tempered glass that is hardened, and I think that what's happening there is that it has less capacity to be hydrated because of the fact that it's hardened that way. And so
that's
at
possible.
the end of the day, I think what we're seeing in these materials is it's the presence of water that decides whether or not it's capable of conducting. Like, I think that it's the permeability of the substances to a conductive material. So it's like the metal is conductive naturally because of its structure. The way that the orbitals inside the metal overlap allows the passage of current. And if you take a super pure piece of glass, a super dry piece of glass, then it loses its ability to conduct. And so what we're seeing is the permeability of these materials to water, because I have an instinct. We're going to go to the desert and we'll take these experiments with us. And I think that they won't work in the desert because it's so dry that the wood...
No, it is the opposite. It is the opposite. In the desert or in a dry season, they work much better because air, when it is humid, air becomes a conductor. So you cannot store electricity in a humid atmosphere. Also because of water, as you said.
Well, I think that the
But,
the electroscope will charge better for this exact same reason. But if you take a wooden rod that, when you're holding it in your hands, in a humid environment will conduct.
Not only that, Anastasia, because here we don't have only the plastic straw as an insulator. The air around needs to be an insulator. And when you have an humid, when it is raining or when it is very hot, very humid, and you have water molecules in the air, you can try to electrify and it immediately discharges.
This is actually, this is funny.
The experiment works better in a dry desert because it is dry, because it has less water around in the air or in the support itself.
But so I think Anastasia, what about the conductors themselves? The conductors themselves. Anastasia is saying like the conductors themselves would be less functional in the dry environment, which I don't know if that's true or not, because they might be able to still retain a fair amount of water even though it evaporates, because the lattice will collapse and trap them inside to some extent.
Yeah, so this is right. So this is actually like in Shiloh's domain. So Shiloh studied this phenomenon called hydration solids, where when you take a substance and you fill it with water, and then you dehydrate that substance, you actually can't pull all the water out of it, even if you dry it for days inside of an oven. And the reason that you can't do that is because the electrostatic interaction between the water and the substance itself is so strong that that evaporation can't pull it out. And so Shiloh's saying that, like, maybe with a really dry substance, you still have enough water that's left over in it in order to be able to act as a conductor. But my point, I think, is that the rubber is an insulator, but I think it has to be a special type of rubber. it has to be a kind of rubber that doesn't have, like, what's the difference between plastic and rubber? Do we know? Because I think that there's something about the lattice structure of the substance and how it holds water. Because you can take an eraser and over time it'll dry out and then it loses its like eraser properties. And so I'm trying to say that like the water is the thing that's doing it.
All of these difference, I really don't know the difference, the reason why they do behave like that. I have some ideas of some of them, but most of them I don't have. I don't know. I
have a feeling that there's like a viscosity element to this too, where like the molecules themselves have to be able to polarize. They need to be able to rotate in order to make this kind of wire happen inside of the material such that, you know, they're able to arrange themselves. I think the metals are really good at repolarizing and reorienting themselves. At least the like relevant valence electron surfaces are able to reorient. But this requires us to develop a material model of electricity, which is probably beyond the scope of this conversation. However,
what I would like to discuss with you, if you wish, is some mysteries which I believe are still hidden in these amber phenomena.
Yeah, let's
amber effect. One of them, normally, if I charge one electroscope positive and the other negative, both strips are up. I have two electroscopes, okay? Suppose these two. And one is positive and the other is negative. The two strips are up. If I just touch them, immediately they neutralize and the strips remain down, okay? How do we explain that? Well, we say it's very simple. Opposite charges attract one another, and we know the law of Coulomb. By the way, I want to show the readers that the Coulomb's works are now available in English. We published a book, Coulomb's Memoirs on Torsion, Electricity, and Magnetism, translated into English. I joined forces with Louis Bucciarelli. He is an emeritus professor of engineering at Massachusetts Institute of Technology. And we did translated all the main memoirs of Coulomb on torsion, electricity, and magnetism into English. And this book is available in PDF in my homepage. And it was also published by this Canadian publisher, Apeiron. So we know the law which makes two opposite electroscope neutralize. But how can I begin with two neutral materials? I make like that, and suppose this is a silk, and this is my plastic tube, okay? Both insulators. The plastic will become negative, and the silk will become positive. How can I separate charges? I don't know. This goes against Coulomb, because I am just doing like that. The two in the beginning, they were neutral. And when I do like that, one becomes negative and the other positive. It goes against Coulomb. Moreover, I don't know the law. Which is the law which applies here? Does it depend on Q1, Q2 over R squared? Does it depend on velocity? Does it depend on pressure? Does it depend on the dielectric constants of these two materials? Does it depend on resistivity of these? I don't know. No one knows.
Go ahead.
I was just going to say, I think we can learn a lot by the fact that friction can generate static charge in these materials.
Yes,
like, there's clearly
something. We know since Plato that we just do like that.
Right. It seems
and you can attract like buddies. But
It
I
seems to.
believe that we still don't know which force is responsible for that.
Well, I wouldn't pin it on a force. So that sounds very Star Warsy, and I would just say that you're doing something to the surface of those atoms. You're setting some sort of state of motion in the surfaces of the atoms that wasn't there before. I mean, you're literally applying a physical pressure to the surface of the atoms, and it's somehow homogenized such that you've sent the atoms into a new state of motion.
Like this
Yes,
is
I agree
this
with
is
you, Shiloh, but we are describing what takes place. But you see, what takes place goes against our most basic law, which is the Coulomb's law. Because if I did begin with a negative and a positive, and if I did do like that, and if it did neutralize, I would say obviously, because opposite charges attract. And I know the law, which is Coulomb. But the film just goes in the opposite direction.
We're not just touching them, right? You're adding friction to the system too.
motion.
Right?
Yes,
Motion.
of course,
You're putting
of
those.
course. I know, Shiloh, but friction does not depend on charge. The static friction, kinetic friction, the friction in air. Static friction is a constant mu times the normal force. And the kinetic friction, it's another constant, the kinetic constant times the normal force. When something is falling in air, in this case, the force depends on the square of the velocity, but the charge does not appear there.
So I think that
by friction, I separate the two charges, but I don't know which expression explains this electrification of these two materials.
Yeah, I think that there's not a mathematical formula that explains
yes,
it.
Yes, there is not.
I mean, the fundamental confusion here is...
This is what I want to call attention now, Shiloh and Anastasia.
But hold on, the fundamental confusion is that the word charge has no physical definition other than some relational attribute, right? Like, the fundamental problem is we don't know what it means to charge a substance. Like, what does that mean? Why is the electron negatively charged and the proton is positively charged?
Yes, we don't know. We don't know many things we don't know, Shiloh. I agree completely with you.
But that seems to be at the heart of the problem.
This is what I want to call attention here.
Yeah, so there's actually an experiment that I think would be very, very useful and relevant here.
Yeah. We have an experiment we really, really want to do, and we will not waste the opportunity to beg the audience to make it happen in their garages.
Okay. So
how is it?
So this goes back to the idea of heat as an imponderable fluid, right? So heat was considered a fluid just like electricity was. And it took until Count Rumford's cannon boring experiments, where he showed that there was more heat. There was basically an inexhaustible source of heat inside of the cannons. Like, you could just keep boiling water with the thing over and over again. Where he was like, oh, that actually might not be a substance that's inside of another substance. It's the motion that's producing the temperature. The friction is producing the heat. And so we boil water. Okay, great. We have this phenomenon of electrostatics, which is produced also by friction. And we're like, man, it's wild. Like, how are these electrons flowing? What is the law that decides it? And I think that a very simple experiment would be an analogy to the Rumford cannon boring experiments, which is like an electrostatic generator, which you test to see, do you ever get to the point, if you take two substances that when you rub them together, you get some kind of triboelectricity, and you isolate them from ground. So basically you have a setup where it's like, imagine that you have like a piece of wool or a piece of silk or whatever, and you're rubbing your glass rod against it. And then you are discharging that system. Will you ever run out of electricity? Like, I don't think that you will ever get to the point where you have depleted the charge from the silk to the glass to ground. Like, this is the system will require the materials themselves to break down, because there's an eternal supply of static electricity in this system as long as you continue to charge it through motion. And what if this experiment does work? What it would suggest is that what we're seeing in terms of charge is we are seeing the surface motion of the substance, of the glass rod, of the plastic
The
rod,
atoms.
of the atoms in that rod, develop some kind of uniform motion, and you can discharge that motion all day long, but there's an infinite quantity of that motion in the substances.
But in this case, what we call these electrified particles, they would not exist.
Right.
Yeah, exactly, yeah.
Yeah, so the hypothesis is the hypothesis being tested is that there is no actual electric particle. It's actually just the state of the surface of the atoms that's in some concerted motion, which is transmitted. Much like the way we used to think about heat as a particle of heat, we still think about the electricity as having a particle of electricity called the electron or the proton or whatever it is. And so we are not, we think that that's not true, but we think that this experiment would solve the question once and for all. We just haven't built the apparatus and we need some help. So,
and it's like, this is actually
someone in the audience should have the interest to try it. That would be great, yes.
Like another thing that's really interesting is that we've been studying cathode ray tubes. And so cathode ray tubes are this famous platform which J.J. Thomson used to demonstrate the existence of this electric particle. And the thing is that there's something that happens inside of these vacuum tubes, which is that if the vacuum tube has some amount of atmosphere in it, less than air, but still plenty of atoms, you don't get cathode rays. You don't get you just basically get this kind of glow discharge because the current is interacting with the atoms that are in the tube, they glow, and in order to actually get a cathode ray, you have to evacuate the tube sufficiently so that there's a small number of atoms where there's a direct path between the cathode and the anode. But if you bring this vacuum down and down and down and down, you lose the ability to produce cathode rays. You lose the ability to arc something from the cathode to the anode. And the way that they solve this is through something that's called thermionic heating, where they actually have to heat the cathode in order to get it to off-gas. And then once it off-gasses, then you get the cathode ray again. And I'm like, this is obvious that what's happening is that in the absence of atoms inside of that tube, that cannot be spooled into this electrified configuration. This motion, you can't get current. And that's why in a perfectly evacuated tube, it's a perfect insulator, and you literally have to heat the cathode in order to send off some small number of atoms into the tube that are then conducting. Like, I think that our fundamental understanding of the electron as this thing that is separate from the atom itself is deeply flawed, because if it was separate from the atom itself, you would assume that in a perfect vacuum with no atoms in the tube whatsoever, you would get perfect conduction, but that's not what you see. You see the opposite.
I would go one step farther and say the chemists already fundamentally understand this, right? They treat the electron as the surface of the atom in some state of motion. Like, that's what everything that they do with their shape binding pockets and all of this comes down to. The chemists understand that the electron is some surface state of the atom. It is the surface of the atom in some state of motion. And it seems like physics and electrical engineering has found it very convenient to use this charged particle accounting balance idea of electricity because it works really well for calculations. But at the end of the day, it makes no physical sense. Like, how in the world does a flying little particle even create this kind of impulse? It boggles the mind.
But I would like to make a comment on what both of you said now and a little before, because we are always talking that when we make like friction like that, we have transfer of electrons, of these particles. These we find in every textbooks when they describe the Amber effect. Oh, it is just a transfer of electrons. But they never explain how should the electrons go to a neutral to one side and not to the other, and so on. But what I would like to discuss here is another mystery of this oldest phenomenon in the history of electricity. This is a supposition that there is a transfer of electrons. Let me read to you there is a book by an English scientist, Harper. It's called Contact and Frictional Electrification. He is a book, 300 pages, full of experiments just on this, okay? How do I electrify my plastic tube? By friction, okay? So in the physicists, they always say, oh, it is a transfer of electrons. I will just read here the first paragraph of this full book full of experiments. It was published by Oxford University Press. The author is Harper, Harper, Contact and Frictional Electrification. So this is the first paragraph of the book. I will read it. A crucial question for the explanation of the production of static charge is whether the charging of insulators comes from a transfer of electrons, of ions, or of both. Then he continues. Montgomery, a certain scientist, would say that the carriers of charge are always electrons. And Loeb, another scientist, that they are generally electrons. A third scientist, Henry, feels that the question is still an open one. Now comes the point of view of the author of the book, Harper. He says, I am of the opinion that a definitive answer can now be given, which is that the carriers are never electrons when the material being charged is strictly an insulator. To me, that is just fascinating. A guy who is specialist in the electrification by friction. And he goes against every textbook because everyone says it is a transfer of electrons between my paper napkin and my plastic tube. And he says it is never electrons. And then he goes a whole book showing 300, 500 experiments at Oxford University. This is fascinating because the physicists, they just take it for granted. They always talk about electrons, but which experiments prove that there is a real transfer of electrons here? And I call your attention, Shiloh and Anastasia. This research continues nowadays. If you look at the internet, maybe the most important, one of the 5 most important chemists nowadays alive is George Whitesides. He is a chemist at Harvard University. He is the guy who wrote the H-index quotations of his works and so on. So he deals with 1,000 different subjects in chemistry. But one of the subjects which he studies is this one. How do I make friction in my hair and this plastic tube becomes electrified? And what these Whitesides has found is that there are not electrons, it is ions, whole ions, not a single electrons. Whole ions are being transferred between the two materials. And which kind of ions depends on which materials you are rubbing with. If you begin with a plastic and paper, it's one kind of ion. If you rub a plastic with my hair, it's another kind of ion. If I rub with my cotton shirt, it's another kind of ion. Moreover, these ions, as you said, Anastasia, have to do with water. Sometimes it is H3O and ions of water. And a simple hydrogen atom, H plus or H3O. And so it is fascinating. So the chemists, they are doing experiments on these phenomena by Plato 2,400 years ago that we still don't understand fully. But all the physicists, they think, no, this is just for kids. Oh, it is electrons. They don't explain how do the electrons would do that. They don't explain which kind of force separate opposite charges. They just don't consider this as a problem. They
That's
put
actually
the Amber effect in the first paragraph of their books, and they go on. But the chemists,
I think it's even weirder that they don't know about the Count Rumford experiment with heat. Like, they've been through this party before. They've been through this before, and they still treat electricity like this magical particle thing.
Well, I mean, if you look at the way that electricity is defined, like you and I went down the rabbit hole of this the other day. Like, what is a Coulomb? What is an ampere? Like, these are definitions that do not point to any kind of like mechanism or internal action. Like, an ampere is defined by the amount of force generated by two wires carrying some amount of current over the course of a second. Like, these are like force-based measurements that are so useful for engineering, because you have an equation that tells you about how a system will behave.
And you can also measure this force, yes.
Yeah, exactly. It's a very neat thing. But then when you start to ask the question of like, okay, well, like, what is a Coulomb? There's no depth to that question. It basically is just like it's.
Well, it gets really circular really fast.
That's kind of what I mean, is the fact that it's like, with depth, you would assume that, like, okay, so if you take an atom and there's some amount of motion that is concentrated in the atom, then that gives you 1 Coulomb of charge when you put it into an electric or magnetic field. But that's not the definition. The definition is a force-based definition of, you will see this amount of deflection when this amount of coulombs are present. But then when you're like, what the hell is a Coulomb? There's no answer to that question.
And my point is that that's exactly the place that people were at with heat prior to the kinetic theory of gases. They were exactly in that same trap. And we're in that same trap again with electricity. And the solution seems kind of obvious to me. But I don't know how. I guess people don't think about these kind of things. People don't know about the cannon boring experiment.
No, I don't think that it's that they don't know. I think that it's just, we ran into something really interesting a while ago where we were trying to understand how polarizers work. Like, so we have this, we're working out this material model of electricity and of light and gravity and everything else. And one of the questions, and we decided that a really good way of going through the explanations was to look at poorly understood phenomena. And so there's this phenomenon that's called the 3-polarizer paradox, where if you take 2 polarizers that are at 90 degrees to each other, they let no light through. But then if you put another 3rd polarizer in between them that's at 45 degrees rather than 90 degrees, all of a sudden you get transmission of light. And it's like, wow, that's so weird. And so everybody has these kind of like nonsensical quantum explanations for it. And so Shaila and I decided that we would come up with a material explanation. And in order to come up with a material explanation, you have to understand how polarizers work. And it was so difficult to get to the bottom of how they worked, because almost every single image on the internet,
all the textbooks
had
the wrong information in it.
Just straight up, like, the pictures were wrong, and you had to go to these electrical engineering forums where people who actually designed polarizers were talking to one another, where you could actually get this information. It was astounding to me. And so I think that when it comes down to this, where you go to a textbook and there's a neat little picture of like the silk and the glass, and the silk has the positive on it and the glass has the negative, you're like, oh, okay, they figured it out. There's no mystery here. There's not a paragraph that says like, hey, this is actually really poorly understood. And I think that that's why people don't delve that deeply into it, because honestly, static electricity isn't really a thing that is used for stuff. Like, we don't really use static electricity. We use almost exclusively electrodynamics for building our systems. And for that, we have really good equations. We have really good material characterization. And so it's
You have field-based explanations for a lot of that too.
Exactly. And so you never get to the point where you have to ask the super basic question of how does this begin?
I know. And this is very interesting because I know with which supposed to be simple experiment, when we try to look at them very deeply, all of them, they have very hidden and very deep mysteries that we should delve into. But I would like to make two other points here. One is about glass that you mentioned, because you see, in every textbooks, they say, when they talk about the amber effects, they usually say it that you have a glass tube that you rub with silk or another material, and then you attract bits of paper. But as I showed to you, modern glass behaves as a conductor. It's very curious because Gray, this Gray who discovered conductors and insulators, he did utilize a glass tube to make his experiments. But if I try to do the experiment with this glass here, rubbing it in paper, in my hair, and holding it in my hand, I will not attract a single bit of paper because this glass behaves as conductor. You see, most kinds of modern glasses, either because of composition or, as you said, Anastasia, because they are hydrophilic, they absorb water on the surface, or because of the way in which they are fabricated. In the end, they behave as conductor. But in the old days, at least in some very specific kinds of glass, like the one which Gray did utilize, some of them by Franklin, by Dufay, they did behave as insulators, very good insulators, because Gray said in one of his memoirs that he did rub his glass tube with his bare hands. And he was holding his glass tube in his hands. And he could make many electrostatic experiments. But if I try with this glass, none of them will work because it behaves as conductors. So I want to bring this to the attention, especially of the audience, if there are teachers of high school or the university. You need to be very careful, because if you say, oh, you make a glass tube, modern glasses, most of them, a window, a plate made of glass, or a becker, most of them, they behave as conductors. And so the experiment will not work. But the student will be frustrated because he will try, it will not work, and he will think that the problem is with him, not with the teacher. But the problem is not with the student. The problem is that the student is trying to do an experiment which nowadays does not work because the material is different from the old ones. But only one author of textbook copies the other, and they don't try themselves. So I call first this attention. The second is another mystery, a very new one. I rub this. It can be a plastic, suppose. I rub this. Suppose it becomes negative, okay? Nowadays, we can carry this plastic tube to an atomic microscope of atomic force. And then we can study the surface of this material, because the charges, they accumulate only in the surface if it is an insulator. They don't go inside, okay? Only in the surface. But what they did find, Anastasia and Shiloh, is very surprising. And this is something for the last 15 years or 10 years. When you analyze in an atomic force microscope, a Kelvin probe, suppose this is negative, then you find that you have negative on the surface of the plastic. Negative, neutral, but then you have some islands of positive charge. then negative, 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 neutron, 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 another island of positive charge. This is called a fractal distribution of charges. Very strange, because it should become either everything negative and neutral, but why should some of them become positive, the opposite? In general, it is negative, but when you are analyzing the very detail at the atomic microscope with a Kelvin probe and so on, you find this fractal distribution. No one can explain that, but it just happens. The same if I charge it with my plumber's tape, so it is positive. Then if you go to an atomic microscope, positive, 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 neutral, neutral, positive, positive, but there are small islands of negative charge. Just like this Chinese game, Go. You have black pieces, but a few of them you have white pieces in the middle, then a lot of black and a few white. So these are the positive and negative charges. It happens. We cannot explain. Just then another, so many mysteries in these 2,500 years old from Plato.
I mean, I think that a big part of the reason that this has been so hard to figure out is because it's hard to see. Like, I think that science progresses quickly and easily in fields where you have some kind of visual feedback. Like, I think about biology all of the time, where at the beginning of the 20th century, we didn't have a model for DNA. We had no idea how inheritance worked, but we did have microscopes and we did have chemistry. And so you could look inside of a cell and you could see, wow, that's weird. There's like these weird, there's components and compartments, and there's something inside of the cell and they appear to change. Like if you can take a slice of onion skin and you can see that each cell is different. And so you can make this model of behavior with an instrument that's fairly straightforward and like a little bit of dye. You can do this at home easily with like dye that you make out of cabbage leaves. That's not the case for electricity, because we're talking literally about atomic phenomena, and the technology that we have for being able to look into the atomic world is so exclusive to this point. You cannot have an atomic force microscope is probably $500,000. It's not something that you can just have in your kitchen and then just like put stuff under it. And you have to be like Shiloh actually did his PhD, like all of the work on hydration solids was with an atomic force microscope. And this is something that takes like many, many months of learning how to use and figuring it out. And it has like complex harmonic features to it. And it's not the domain of a hobbyist. But I think light microscopes and biology lends itself more to the domain of the hobbyist. And so now, as you're saying that we're having these new experiments done where we're showing the actual behavior of the atoms, then now this may lead us to the next level. But it's like these discoveries require some kind of new insight that isn't available at the macro scale.
As you said, sometimes extremely expensive, only in a very specific research laboratories can afford to have them. And so the knowledge becomes concentrated once more in the hands of a few. So it happens.
Yeah, what were you going to say?
If you allow me, Shiloh and Anastasia, I would like to say two things. The first, I would say ask the people in the audience who is watching me two things. First, if you could share this video with high school teachers, university teachers of physics, and so on, because these experiments, these hands-on experiments, I have been teaching physics for more than 40 years, and I know no better way for science grasping really the contents of science and never to get out of you. It belongs to you after you make these experiments. Then to make them with your own hands. So you can make an electroscope, you can make an electric pendulum, you can make a versorium, and so on. So, and you don't need even the laboratory of the school, because you can do that at home, as you said, Anastasia, at your kitchen. And so I ask, please share this video with any physics teacher or at the university, high school, and so on. But moreover, try to suggest that the students themselves perform the experiments. When this book of mine, this here, it came out of courses which I gave in Brazil for fundamental level teachers, for children, and for high school teachers. And normally we did make these classes on Saturdays. So we spend 4 hours with 40 teachers and so on. So I did teach each one of them how to build an electric pendulum, a versorium, an electroscope. Then the teachers themselves made the experiments so that they could bring that to their students. And I always said that the students themselves, they should build these equipment and they should keep them as a gift for them so that they can carry home, they can show their parents, they can show their colleagues, their families, they can repeat the experiments and they become immediately scientists because you immediately begin to ask questions. But if you make yourself the equipment, you answer them. You go and try. Oh, a leaf, is it a conductor or an insulator? Try. You try it immediately. Coca-Cola or orange juice, is it a floor? Is it a conductor? Or you just go and try. And that is fascinating. And the second thing is, I would
can I
really
just
love.
can I just add in one thing really quick? I think the coolest
Yes?
part of this series has been that we walked through the preliminary experiments by the sort of venerable forefathers, and we saw how they drew their conclusions. But then at the very end, there's an absolute paradox which emerges, which is how does your attraction, contact, repulsion not abrogate the entire thing at the beginning, at the very first experiment when you're touching the amber to the wool and doing the charge generation in the first place? You're making your magic wand. So it's funny because the magic wand is still the outstanding mystery. Like it's the very first piece, and it's still the biggest mystery at the end of the explanation set. So that's really cool.
Sure, Shiloh. I agree with you. And that's fascinating because I am so fascinated by these things because we have so many extremely deep questions with these very basic experiments. I'm not talking about high frequency electromagnetic waves in a torsional space or in a very specific kind of chiral material and so on. No, this very basic experiment by Plato 2,400 years ago. There are so many things that we still don't understand correctly. And so,
absolutely.
And I don't know a better way of teaching science than this way, that the student himself builds the equipment and performs the experiment and carries it home as a gift.
And carries home the mysteries that remain. Like I had this feeling when I was doing experiments in high school or college where you're going through the process of doing it, and it's pretty cool. I agree. You become familiar with it, but you're left with the feeling like all the problems have been solved. Every single laboratory course I ever took in college and in high school, it was always like, well, this brilliant person solved this, and now we understand blah, blah, blah. And so I never, ever was exposed to the mysteries of these phenomena. And that's what I think is most exciting about this experiment.
I agree completely with you, Shiloh. And for this reason, this book has 2 volumes. And the second volume, the same title, but volume 2. The last chapter of the second volume is called The Mysteries of the Amber Effect. The oldest phenomena of electricity and mysteries that I myself really don't know the answers. And I said many of them. Some of them I did say here, present here. But I have many other from this amber effect. Not for other phenomena, for AC current and so on, but for this amber effect. So I made this on purpose, Shiloh, as you said, because I hope that one of the readers of this book will get an interest and maybe we will have another Coulomb who will find this, as I said, the
Well,
law
I will
how
say,
they do.
Andre, that we are finishing up a book that will cover our own particular solution to this phenomena, and it would be really fun once our book comes out, probably in the next few months. Fingers crossed. We
Wow,
thought we'd
few
finish it by
months
the end of the
only.
summer, but we got busy. But we will send you our book once we've finished, and maybe we can come back and have you either tell us why we're wrong, or maybe you'll just be excited.
I
Do you
mean,
have
there's
the title already or not yet?
The title is Paradox Lost.
Okay, I like it.
And it will be we haven't figured out totally, we haven't nailed the subtitle yet, but it will be an examination of the loss of material mediators throughout fundamental physics and a potential path forward. So we have some proposals. We obviously haven't solved everything, but we have, this is one of the things that we take aim at, is the physical mechanism of electricity. And of course, as I've alluded to in this conversation several times, we think that it is some change in the surface motion of the atoms themselves. But we'll break all that down, and maybe we can try on some of our ideas on you next time.
I look forward in reading it. And so just my last remark, if you allow me, just I really love this way of teaching. To me, it's much better than what we do, only mathematical formulas in the blackboard, or discussing only philosophy of science or peer-to-peer. I have seen many different ways of teaching science, but I really don't know a better way than this one of performing hands-on experiments mixed with the history of science. And so this is what I try to do with this book. And I would love if there is suppose a Chinese physicist watching us, who knows, who would like to translate it into Chinese or into Spanish or into other languages, just to get in touch. You see my email, my homepage, and that would be great, because this, to me, it's the most effective way of bringing science that we need so much nowadays, especially in third world countries, where the teaching is terrible, just formulas in the blackboard. But here we can go very deeply into science with hands-on experiments mixed with history of science. So I thank both of you very much, because you bring people to open these to others, to show it to others. So what you are doing, Shiloh and Anastasia, is wonderful, because you are opening this whole new world to many people all over the world. And so what you are doing is invaluable. So I'm very happy with this new opportunity that you gave me. And now I look forward to reading and thinking about your new book, maybe this year or next year. Just keep me informed.
Yeah, of course. I mean, I love the simplicity of these demonstrations, and I'm struck by the fact that we didn't finish. Like, there's a bunch of stuff that was in the packet that you gave us that we didn't get to. And
But
so,
too many things for just, we read almost 3 hours now, so too many things. But we saw many experiments here. I think that was, people can have a feeling of what is inside of these books. And you as guests, not only online, but personally, like in Portugal, you are just wonderful people. So thank you very much for
the
opportunity.
feeling is mutual, Andre. And yeah, of course, folks, go back and listen to the other podcasts we've done with Andre, and we'll link those down below.
and I honestly, there's so many more conversations that we could have. Like I would love to go through some of Coulomb's early work and talk about the actual experimental process by which he came up with his laws. Like, I think that getting as many people as possible to understand the basics, like this format where you have demonstrations, and then we can look at the phenomena.
What you said, for instance, I know that Coulomb not only found the Coulomb's law, Q1, Q2 over R square, but the law of his torsion balance. Okay? He created the torsion balance, but he found the law that the torsion is proportional to the angle, but there is also a thread can be a metal thread or a silk thread. And it depends on the length of the thread, depends on the force power of the radius of the diameter of the thread. I always curious, how could he find this force power and so on? But now his papers, they are available in English, in the original French and in English now. So anyone can go there and read and repeat his experiments. They are fascinating, Anastasia. Very simple. With well, one day we talk about it.
Yeah, I think that there's so much ground to cover. You're a rare bird, Andre. Like you have such passion, you have such a depth of historical knowledge, and like you said, having the experiments in front of you so you can contemplate them and you can do them and you can go away and think about what they mean and what they reveal about the world is so powerful. And I'm glad that you're part of our community and that you have this to bring to
And
us.
to me,
Thank
it's
you.
so myself when I found how did they discover positive and negative charge? Oh, it's this Harry Potter experiment. Oh my goodness, we don't see that in the textbooks, but so fascinating, and we can repeat that in front of the students. They love it immediately. So
It's very
great.
Absolutely. Well, we'll let you get on with your day, Andre, and we'll get you back here very soon. It's always fun to hang out with you.
Thank you very much, both of you. Great
Absolutely.
guests.
Thank you. Bye, everybody.
Bye, everybody.
Bye bye.